Hey everyone, welcome to another deep dive video with me and Erik. This week we're looking at the Dungeons and Dragons character exercise. If you've not done this one yet, the idea is that you have to generate a character with all their properties, things like strength and dexterity, randomized based on the correct formula of rolling 4 die and then taking away the lowest number and then adding the others together. And there's also a special rule for your hit points where you have to use a constitution modifier that we'll look at as well. We're going to be looking at a load of solutions in this, but the main focus for this video is random numbers and different ways of doing randomization, understanding pseudo-randomization, seeds. We're looking at some generator functions in Haskell later. We've got a whole load of stuff to look at. And as always, Erik's going to be leading us through stuff. So we'll dig straight in. The first solution we're looking at is in Kotlin. This is the most sort of straightforward solution, I guess, Erik. This is the probably the simplest and cleanest to read, I think, of all the ones we've got. Talk us through it.
Yeah, so in Kotlin, you can have a class with, properties or values, or whatever you call it. So for strength and dexterity, etc. And they will only, in this case, this domain, they should only be generated once. So after that, they're like fixed. So you roll the dice for all of those properties and then they're fixed. So in Kotlin, the way that you can do this is by setting those properties as vals, so VAL, which means that they're immutable. They can't change. Whereas if you would be using var, they would be mutable and you could be changing them. So the very fact that we're using val indicates that once you created an instance of this class, its properties will all stay the same for its entire lifetime. So that's very important. And then in many languages, you would maybe do this in the constructor. So you would have fields that you define, and then you have a constructor that sets them. But Kotlin has, a bit of syntactic sugar around it that allows you to do it sort of inline in the property, where you can directly assign it a value. And that value in this case is assigned by calling the ability method. And the method itself is defined in what Kotlin calls a companion object. And you can sort of, without going into that, you can sort of read that as everything that's within that companion object are static methods. It's not entirely true, but that's sort of what you can think of it. So you can call those methods with D&D character dot ability without having an instance. And then from within the class, you don't need that D&D character prefix. So you have sort of like helper methods. Maybe that's a better way to think about it. And there are two here. So the second one is the easiest. It's modifier, which are the D&D rules. So you get a score. So something between 3 and 18. And then you divide it by 2. Minus 5, you get the result. So that's a little bit different from how it's actually specified in the instructions, but it's still valid. So it has the same result. And what we'll see here is that we can just use slash on integers and we get back a new integer, but that's not something that generally holds for all the languages. And we'll see other languages for which it doesn't hold. But do be aware that if you divide an integer by another integer, you might get back a different type, a floating point type, but that's not the case here. We just get back an integer, so we're golden. Of course, we haven't done anything yet with randomness, so maybe we should try and get that rolling. So that's with the ability function method. So what we want to do is we're going to roll 4 dice. Each dice has between 1 and 6, a value of between 1 and 6, and we want to omit the lowest value. So the way that this is done is creating a list of 4 elements, and then between those square braces is the code that is executed to get the value of each of those elements. In this case, we're doing random.nextInt, passing it a range, so that dot syntax is a range, starts at 1, ends at 6. Then we do sorted, so we sort the values, which means that the lowest value is the first value, and the highest value is the last one. So if we drop the first value, we are left with a list of 3 elements, and those are all but the lowest value. So we can just sum it, and then we have our ability score. Many people do it like this. There's not much variation here, actually. So you see this a lot.
Yeah. Yeah, this is the nice simple way. I imagine most people watching this video, sort of the first approach they'll have taken will be this one. So let's go a bit deeper, Erik. So this next one is in Nim, and there's a few extra bits and pieces we're gonna look at here. So I see we start off by importing maths and random. Talk us through what we see here.
Yeah, so in where Kotlin had like the class and the initialization of the properties, so within them, in this case, they're extracted. So you get the definition of the type first on line 3. So you get an object with a couple of properties, all integers, but you don't get anything assigning values to them. We'll do that later on. But first, on line 12, there is a very, very important call, and that's called randomize. So this is where we have to talk about randomness in computers. So true randomness is not really possible on a computer because computers are, well, deterministic. So there is an algorithm that you can run. And if you've written code probably if you're watching this video, you know that if you run it with the same input, you get the same output. So random number generators are still just random algorithms. So if you put the same thing in, you get the same thing out. They just do very fancy math with, I don't know, bitwise ands or whatever. There's a lot of stuff going on there to make it appear random, but there's not truly random, which is why randomness in computers is pseudo randomness. So it looks random, but if you actually look at it from a mathematical viewpoint, so which means that everything is equally likely, then you would quickly find out that actually it isn't proper randomness in computers. But that doesn't mean that it's not useful, because pseudo-random numbers are all over the place. We're using them all over the place. They're definitely very, very helpful, but there are things to be aware of. And one of the things how these pseudo-random generators work is to, they start out with a seed value. We don't just want to pass in the same value every time. So that value that it's sort of basing itself off is called a seed. And if you change the seed, then you get different values. But if you have the same seed, you get the same values every single time. So that's also a way in which random numbers in a computer can be very useful. So if you store that seed somewhere, you can give it to somebody else on the other side of the world. And if they're using the same algorithm, they can repeat what you were doing. So they can repeat the same, they can generate the same random numbers. They're not really random anymore, but that's dependent on the seed. So the seed is very, very important. And what randomize is doing here is to set that seed to a random value. I'm not entirely sure how Nim does it, but there are lots of possibilities. For example, looking at the CPU clock, the number of ticks. You don't want seconds. So if you want to do seconds, which some languages have also done, old languages, then if you run the same program within the same second, you would get the exact same results. So don't do that. But if you use ticks, it is far less likely. But even ticks are not that precise. So if you really, really, really value your randomness, you'll probably do something with, you would want to do something with atomic decay or whatever, some truly random process, and then somehow access that. But that's not what we're going to do here. We're not going to do anything fancy like that. But seeding and making sure that you do seed your program, although some languages do it for you automatically, but Nim requires you to do it like proper with randomize. It's also in the docs, so you can you'll be notified for that. But key takeaway: seeding is important because we are using pseudo-random number generators, which means that if you put the same thing in the same seed, you get the same random sequence. You still get what looks like a random sequence, but you'll get the same sequence every single time if you use the same seed. So that was my short introduction to pseudo-randomness. Maybe I'll explain later on a use case where you really, really, really want to have this proper, but we'll use a different solution for that. So back to this Nim solution. Let's actually generate random values. So that's being done in ability. Ability is defined as a proc, whereas modifier below is defined as a func. And that's a property of Nim where you can have functions are things without side effects. So things that when you run them every single time, they get the same result. Whereas procs they can have side effects and they can use state basically, and that seed is like a state. So the very fact that we are generating random numbers within ability means that we're using the seed, which we don't control. So that means we must be marking it as a proc. So something that could that is not deterministic, which is fine in this case, of course. But you have to set it in the definition of the function. So what is being done to generate the actual values is they start out with an array of 4 values, and then for each of those roles, so with you can do a for with m items, means you get like a reference into the array. You can set its value by going rand, and then again with the range, it's almost the same syntax as Kotlin, also with the double dots. So that's fine. The way that we don't do sorting here. We sum all 4 of the numbers, and then we subtract the lowest value, which is of course the same thing. I would argue this is even more directly related to how it's phrased in the instructions, but both are fine. So, and then there's hardly much left to say, except for on line 20, you see that we don't do slash, so we don't do division with a slash. There's a separate function called floor div, and it's probably named differently in your language, but this is for the reason that I told you. When you do division with the slash, you might get back a floating point number, whereas you want an integer, and floor div will guarantee that you get back an integer. And floor means rounding down, of course, so which is the spec. And then to generate the actual character. Sorry.
Sorry, I was just going to say this is the algorithm as it's specified as well. In the previous one, we saw the sort of divided by 2 minus 5 or whatever. Here we're seeing minus 10 divided by 2, just to explain that for anyone watching.
Yeah, absolutely correct. So this is, I think, the way that it's specified in the instructions.
Yeah.
And then to generate the actual character, and within the init character proc, it's just, it's such a function call. There's nothing much to it except for the fact that you have to specify all of its values at once to create it. So you have to calculate the constitution first, because you need that for calculating the hit points. They reuse the modifier function, which is great. So nothing special here, but the key part is here. They use seeding to make sure that they get different results every time the application runs.
This line here you mentioned, Erik, about summing and then taking away the lowest. I guess I was thinking originally that maybe this is actually more performant as well, because you don't have to go through and sort everything. But I guess you probably are sorting them anyway via the min call. So yeah, I'm not sure if that would be more performant or not. You said you think it's closer to what's said in the instructions, but what do you think?
Yeah, you need to do 2 iterations here, because both sum and minus will have to iterate over all of them. There are just 4 of them, so I'm not sure how bad that is.
Yeah, I mean, it's a tiny thing.
Yeah. So it might actually be quicker than actually sorting, I think. So this is easier. If I'm thinking about this as a CPU, it's like, I'm just going to loop through it and have a state thingy that I'm updating with either a sum or a minus, the lowest value. Benchmarking.
So let's jump to Racket, which is our next one. So this is I guess a Lispy version, Erik.
It is.
Lots of brackets in here. Yeah. Talk us through it.
So there are just a couple of things that stand out here. So for one, I really like how in Racket the definition of the struct is so succinct. So you have line 8, you say struct character, and then you have a list of all those properties, and that's it. So there's hardly any overhead there, except for maybe a couple of parentheses. Then within the ability, we don't need to go into that specific detail. It's basically doing the sorting and then dropping the first one. So rest means everything but the first element. The only thing that's worth mentioning is that you have random 6 there somewhere. If you can highlight that. And then there's an add 1 before it. And this is because many many random number generators are exclusive with the number. So this will generate 0 to 5 probably, and then add 1. So that might be something that you need to check, whether or not that upper bound is inclusive or exclusive. So that is not always the case. There's no like one size fits all there, but just check the documentation. And then, you see here that if your language does not have a specific on line 16, sorry, I'm mentioning that is the modifier function. We're doing slash, so we're doing division, and we get back a floating point number, and then we explicitly do floor to get the integer version of it. So this is the way that you do it if your language does not have a built-in function or operator to do integer division. And then finally, on line 20, just creating a new character is just there. It's a function basically. So character is the function, and then all those ability between parentheses are calls to the ability function. So you can see how it is actually quite easy here. But just want to show off that how elegant Lisp can be too. So
it's really nice.
If you're not used to Lisp, you can probably not read the ability function very well, but once you get used to it a little bit, you'll appreciate its elegance, I would argue.
Yeah, for sure. It's still definitely like a read, starting on the inside and working out, isn't it? Is the way to do it. Well, although, yeah, I suppose it sort of is. So this is just making a list of size 4, presumably, Erik?
Yeah. And then calling that those things between parentheses on the right. I must admit, though, that those other two solutions that we looked at used ranges. So they did 1 ... 6, and I find that far more readable than this, because you don't know just by seeing this whether or not it's inclusive or exclusive. I can assume it's not, because it's at 1 before, but it's I always prefer those ranges because you can see both ends, even though you have inclusive exclusive ranges too. But yeah.
This is quite nice as well, being able to sort on less than.
Yeah.
As a thing. It's quite a nice sort of compact way of specifying that.
Yeah, it is. Yeah.
Cool. Okay. So if you don't know Lisp, you don't know how to read this very easily, maybe pause the video and just take a few seconds. It's not that hard, but it does, as Erik said, just take a little bit of mental gymnastics the first couple of times you look at Lispy languages. But let's move on to one of Glenn's solutions. We nearly always have one of Glenn's solutions sneaking somewhere, and this is Tickle, as it's pronounced, Erik.
Yeah.
So yeah, talk us through what we're seeing here.
So there's nothing that interesting about the modifier function, except for that this time they're using int to do like the conversion to an integer. So that will floor around, which it has in a nice documentation, nice comment. One thing I liked about this solution is that, which few people do, is that they have a separate procedure to do a dice roll. So it's called D6, which is short for, a dice with 6 faces. And then there's a bit of logic, of course, to get the randomness. But it is different from the other solutions in that we have rand call, but we multiply it by some value. We multiply it by 6. And that is because in many languages, rand returns a value between 1 and 0. And that's usually exclusive with 1.0. So the upper value is 0.99. So that's why you also have to have that 1 plus value. I think there is an issue here with that 6 value being less likely. So you have to, it depends a bit on the rounding. But I have a very nice video that we will be linking you to that goes a bit more into detail how working with rand and with floating point and then converting it to an integer range, there are some gotchas there. But I'm going to wait a little bit with going more into that. And then for generating
this is
ability,
this is very common though, isn't it?
Yeah,
I was just going to say this is very very common. I mean, I do this in Ruby all the time. This sort of you've got that just starting between 0 and 1, then you can just multiply it by whatever you want that range to be, and then
and that's
floor
mostly
it
fine in most of the use cases.
Yeah.
We hardly ever need.
Could you? I mean, yeah. Why would you need something not to do it? I guess you could do a dot, like instead, like this is effectively flooring it and then adding 1. So you could, I guess, just do a ceiling instead here to raise it up. But maybe that's what you're saying with some of the issues with that, Erik, that, that video will link to.
Yeah.
Okay.
It is.
Ability then.
Well, yeah, ability has some Tcl specific code where dice is a list of 4 calls to that procedure function. So that D6 procedure, sorry. And then you get the plus applied to, I think that brace's star thing is converting it into individual, so the list to individual arguments. So that's like, maybe you could think of it as a reducer or something like that, if that helps. But it just gets you the sum of the dice. So, and then you get the minimum. So this is the sum minus version. And then the skip over hit points because that's, well, simple. And then for the character, this is something that not all languages have, like this container concept, like an object or maybe like a structure or something, whatever your language calls it. So for those languages, what's often the case that this exercise will require you to create an object or a dictionary or a map, whatever the terminology is that your language uses. And Tcl is very dynamic. So on line 36, we define a variable character, which is initially just an empty dictionary. And then we're going to loop over the characteristics, which were defined at the top. And then we're going to set all of them to the result of calling the ability procedure. So this is very dynamic, just setting fields in a dictionary. And there are many languages that have this exercise that require you to do something like that. But nice. Yeah, well, and then you just have to set the hit points, of course. So you get the constitution, and then, well, it's all easy enough, I guess. The key part is that it's very dynamic, but we'll see more dynamic solutions in a sec.
Yeah, I always like it when you have like reducing on a plus as a way of summing things. I think that's always quite a nice way of doing things. Cool. This was the characteristics as well that you mentioned. Okay, so let's look at Python. This is, as you said, very dynamic version here, Erik. Talk us through it.
Yeah, it's similar to what Tcl does, where you had like a definition of the abilities, the properties separately, and then you iterate over those to set values. Only this time we're doing it not on a dictionary, but on an actual class. So underscore init underscore is a special method that's called when a new instance of that class is created. And then what's being done here, so you can see it as like the constructor if you're more familiar with that term. And then Python's dynamic nature allows you don't have to specify all these properties up front. You can just dynamically add them. So you have on line 14 a for loop iterating over all those abilities defined in the tuple at the top. And then you set the attributes by just calling the ability function. So you're basically setting the property with the name of the property to an ability value that's randomly generated. So you're adding values to that character that you can then access, or the public, and that's that is very dynamic. The downside is that it's sort of indirect, so you have to go back up to see what are the actual abilities. But it's a small downside because the logic is the same for all 6 abilities. So I can see why you maybe want to do it like this.
Yeah. We haven't seen this syntax, I don't think, yet today, as a way of just getting the sort of an alternative to dropping the first one or doing the sum minus. It's
slicing.
Just summing on the second element all the way to the end is what that means for anyone that's not familiar. It's just a range using a colon rather than 2 dots. And again, we're seeing that here the random int version rather than the version we just looked at with the multiplication. Yeah. Nice. Yeah, when I did my
They
Ruby
have
version, one of these.
you see a special
Go
/ operator on line 9.
on.
I forgot to mention that. So this is an example of a special operator for integer division.
Yeah. Yeah, when I was doing my Ruby one, I did a similar thing, but rather than setting attributes on the character, I just defined arbitrary methods, just singleton methods that did the same thing. I think if you come from a dynamic language, this is probably, whenever you see a list of things that have got similar behaviors, your mind immediately sort of drives towards, setting attributes dynamically or creating methods dynamically or something like that. It feels one of the advantages of dynamic languages is that you can do this nicely. Cool. Okay, so moving on to looking at some more hardcore stuff with randomization, Erik. This is C++. And here we are doing this sort of slightly intimidating looking bit of code. Talk us through what's happening here.
Yeah, so I mentioned that pseudo-randoms are using algorithms to generate things and that they might not be the best of solutions. And for example, we want to generate a number between 1 and 6. So where people, it might be that a random number generator is maybe 16-bit signed integers. So the highest value that it can generate is 32,767. And the very fact that it ends on 67, that is important because what many people do is they'll generate a random value and then they use the modulo operator to get it within a range. So if you would do random modulo 6, you would get 0, 1, 2, 3, 4, or 5. And then you can add 1 to it, which seems to be fine. You get the result that you want within the range. But the problem is, and it's not really a problem in this specific exercise, but a more general problem, is that not every number is equally likely. So if you go back, if you generate 0 up until 6, if the number would end at 6 and you do modulo 6, you get fine distribution. For 12, similar things. So a 1 is equally likely as a 2 when the number that you that was generated is in the range that is a multiple of 6. So does that make any sense?
Yeah, it does. So what you're saying is because we're not ending on a round number at the end of the possible range of things, there's a slightly different chance that when you divide by that, you're not going to get numbers that would have been above that end number.
Yeah, but I can probably make it very concrete. So suppose we would have a random number generator that would generate in the range of a byte, or maybe just 8. So you would generate 1 up until 7. So those are the 8 values that it can generate. So if you do modulo 6, well, the result is always between 1 and 5. So that's fine. But if you write it out, so if you get a 0, modulo 6 is a 0. 1 is a 1, 2 is a 2, 3 is a 4, 3, 4 is a 4, 5 is a 5. But 6 is again a 0, 7 is a 1. So we get 4 occasions where we get numbers 3. So numbers 3, 4, 5, and 2 are all generated once, but numbers 0 and 1 are generated twice. So they are more likely.
Yeah.
So this is a general problem. If you use modulo and that number that's being generated from is it the multiple of the thing that you are moduloing, then you get this problem. It's like the pigeonhole principle. If you have an unequal number of holes. So that's one of the problems. And we will link in this video a very nice video, a rant considered harmful. I find it a very funny video. That person explains it very, very well. But how using the default random functionality can lead you into this like false sense of having random numbers. So instead, the C++ people have come up with solutions to make this proper randomly. So there's a couple of things here. So you have on line 9, you have std : mt 199937. So it's a very weird name. MT stands for Mersenne Twister, which is a pseudo-random number generator. But it's initialized or seeded with a random device. So this will be probably not the system clock, but something more random. So you
Mm-hmm.
should be reading that as seeded with a properly random value, so that you get a higher chance of
Mm-hmm.
proper random values. And then if we go
Mm-hmm.
down a bit, so we can ignore the modifier and floor division bits. On line 27 is one of the other key parts. That's a uniform
Mm-hmm.
int distribution generator, basically. So
Mm-hmm.
what that means is, I mentioned that example where a 0 and a 1 were more likely than the other numbers. So that is not true randomness. In
Mm-hmm.
true randomness, all the numbers are equally likely. And uniform distribution
Mm-hmm.
means that all the numbers are equally likely. So
Mm-hmm.
this implementation is such that it tries to guarantee that all the numbers are equally likely. So you get it will still be a pseudo random number generated. You can't get around that really, but it will be more random than the older solution using, for example, rand. And there has to be a
Mm-hmm.
lot of clever things that it uses, but you don't need to bother with that. You can just use uniform int distribution, and you'll get more random
Mm-hmm.
solutions than you would with just using the default random thing. And you might be wondering, why would I
Nice.
ever care about this? I've never had a problem with this,
Mm-hmm.
but if you make this very concrete, suppose um, you were having an online poker hand simulator, so where people can
Mm-hmm.
play, and you are the casino or whatever. You want things to be properly random. You don't want people knowing
Mm-hmm.
that maybe a 10 is more likely than a 9, because that might not
Mm-hmm.
matter for just a couple of games. But if you play a ton of games, this will cost you, because people can figure that out. And this
Mm-hmm.
has happened. So it's not like a theoretical thing.
Mm-hmm.
People have done this sort of analysis by just analyzing all the games that they played, and then, well,
Mm-hmm.
plotting them so they could see which one of the cards were more likely than others. So there was a skew there somewhere. So you could use that information to basically tilt things in your favor. So when
Mm-hmm.
you want to have randomness and there's money involved, you
Mm-hmm.
definitely want to be very careful that you are generating as random things as possible. So, but we
Yeah.
don't test that here, so don't worry about this
No,
exercise. But
we're not trying to worry too much about that.
no,
But yeah,
but it's still good
that's the.
to do this.
I was going to say that. Yeah, that's the point of these sorts of exercises. It's not that you're trying to. Sometimes people, I think, get a bit confused and they're like, "Well, you're not testing for all of these things." And it's like the point of the exercise isn't that you're trying to create something that can hold up against the Nevada Gaming Council standards. It's that you're understanding how to use this in case there's a time in your career you do need that. And so, yeah, I think even though it doesn't matter too much for your Dungeons and Dragons game, understanding these core principles is, I think, the key thing here, Erik.
By the way,
and so we're creating this distribution. Go on.
I just noted that on the right side, you actually see that modulo thingy that I just mentioned. So with the solution to the right, I don't know if you can see that on the screen.
Oh, you won't be able to see that on the
video.
People won't be able to see that on the thing, but yeah, someone else does. Yeah, someone does do that in a different.
It's the exact same thing that I just described. So rand percentage.
You can bring it up. Yeah.
Yeah.
So yeah, we're doing that here. Erik just noticed this on the off the screen that you can see on the video,
sorry.
But yeah, just doing this, we now know from what Erik's just said that this will skew, not to a massive degree, a very, very tiny degree, but it will skew results towards, I guess, just towards 0 if it ends in 67, right? So just towards the first.
Well, yeah.
One.
Yeah.
But
have to do
let's go back to ours. So we've got this distribution. Then we're calling it with the. Just to remind people,
that random number.
This function called above. Yeah. So this is bringing those two concepts together in this line 32.
Yeah. So it's both parameterized. So we have a uniform distribution thingy that takes a random number generator and then uses it to generate the numbers. Well, we mentioned that what is faster, so that sorting or that summing minus. So probably this one wins because this is a single iteration that does both. So you define both the sum and the minus value, and you both update them within the loop. So you only have to iterate once. So I'm guessing this one wins because it just does one.
Yes,
iteration.
I think this will definitely win. Yeah. Yeah, nice. Cool. I think everything else is pretty standard on here, Erik.
Yeah.
they do define floor division as a standalone function as well. That's then used, which is interesting. That C++ doesn't have this built in. It probably does in some library, but surprised it's not in the standard lib.
Might be that it's in the later standard library versions, because we just had a discussion where it's harder to update C++ to the latest version because of, well, what distributions package. But so it might be there already.
It's one of the hardest languages to keep updated. Okay, cool. Very nice. So we've got
that was the
other C++ one. Yeah. We've got one more, which is Haskell. And this one is really looking not so much at the randomness, but at Haskell's laziness. And one of the things Haskell is famous for is being a lazy language, and we can see that in these generators. So Erik, talk us through what we're seeing here. Where should we start?
Yeah, we're actually delegating that randomness to a library, so good for us. But the way that this is structured is different. So that character definition, line 10 up until 19, is very reminiscent to what you've seen before. So the modifier too is just a function taking an integer with a little bit of syntactic sugar, where if you have a function call, you can put it between backticks so that you can do an infix notation where it's between the numbers. Otherwise, it would have to be before the left number. But that's just Haskell syntax, so that's nice. But on line 24, things start to get different. So ability is not a function that just returns an integer. It returns a generator of integers. So this is like an intermediate layer. So a generator is a thing that can generate a value, but it's not actually a value itself. So you have to, if you create a generator, then you have something that you can use to generate values. It is not a value itself. So the generator is not an integer. It's a thing that you can ask for an integer, and that will be a random integer. But you can put constraints on it, and that's what's being done here. So that do bit, and then you may not read Haskell very well, but just read that as doing the same thing that we did before, with generating 4 die6 rolls, and then having the minimum and the sum and returning that. But the key part is that this is sort of this is code that only gets executed once you ask the generator for a value. So if you call the ability function, it doesn't really do anything for you to generate an integer. You get back a thing that you can use to generate abilities, and that's what you were now highlighting. So character too is not returning a character, but a generator of characters. And this is where the generator framework can be very powerful, because you can compose these generators. So you can build a small one, and then you can build a bigger one by using that. So this is exactly what's being done here. So with roll d6, we get so on line 32, we're returning a generator, but this time we are using one of the built-in generators, which is another benefit of using the generator framework. So there is a choose thing that gives you back this, just a regular function, but that function gives you a generator of integers for that range. So we don't have anything with randomness or seeding. That's all being offloaded to that generator framework. But the idea is that you can build on all these basic generators, and to build up more complex generators, and maybe build even more complex generators on top of that, all the while still writing code that looks like it's just, it's almost imperative-like, which is Monad's do notation. It makes it feel like it's like a sequential nice thingy. But actually, under the hood, this will only be executed once you actually do something with the generator to generate a value. So there's an additional layer between it. And you not only have the benefit of getting to compose all these things in a very nice way. So I like lines 36 up until 41 that are very, declarative, I would argue. So composability is a major benefit. But another major benefit is that Haskell has a built-in solution to test these things in a manner that is probably different than what you're used to. So can you open that test file, Jeremy? So this is the test file for this specific exercise. And if you go down a little bit, so you go down to line 25, there is a thing called ability generates values within range. So, okay, this is just to check whether or not that ability is within 3 to 18. So ability within range, if you go down a little bit, then it is defined as just a regular function. So this is just putting in an int and getting back a bool. So this is just checking whether or not it meets the range criteria. So there's nothing fancy about this. So just to get that out of the way. But if we go back again, the thing about this this test is there are no concrete values. So what it says for all ability within range, and that reads well almost like prose, and that is passed into a thing that's called a property. And if you've never heard of property-based testing, this is property-based testing. And property-based testing means that you don't specify concrete values. You sort of say you generate random values and then check if these properties hold. So they're not just if x is what, I don't know, 1, then you get back 7. But you would argue like if you pass in a number, the result is greater than the input number, something like that. So it's more you are reasoning about properties than all about specific examples. And the benefits of this is that it will generate all random values, and then it will try to find a version where it doesn't work. And if it does so, it can do something that's called shrinking, where it tries to find the minimal counterexample. It's not really that applicable here. But there is a whole bunch of stuff going on with property-based testing that can be incredibly powerful and give you a higher confidence in the working of your code, because you're not saying this code, I know that this code is tested against these test values, but in principle, if you just have specific values, you only know that your code works for those values. You sort of have to trust that it also works for the others. But if you do it like a different way, so if you have a property-based test, you just maybe sort of describe it at a higher level, and then have the test framework generate all the values for you. Of course, you can limit the values, and in this case, we pass in a specific generator ourselves, which is the ability. So the test framework will call the ability generator and ask it for values, for actual values, and then check if they are passing that function that we just called. So that's property-based testing. That is a very powerful way of dealing with things that when you want to get a high confidence in your code, it can be tricky at first, but I highly recommend you at least trying property-based testing at least once to see if it suits your purposes, because I've done a bit of property-based testing myself, and I really liked it. But it is somewhat odd to start at first. But you don't have to know much about it because it will all be in the test suite. But that is another benefit.
Yeah. And so just to like clarify this, Erik, just to re-go through what you said a little bit maybe, but we've got this property testing framework, and we're saying that for every time this ability is called, and this is the ability that we just saw defined over here in the source code. So we're just going to keep calling this function over and over again for however many times that it is specified to do so. And for each of those things, we're then going to call this ability with range. And then we're doing exactly the same for character. We're coming over here. We've got this character generator that we've built, that we've imported. We call this. Every time we call this, we come down to character is valid, and we're doing exactly the same, just checking that for each of the abilities in there, they are within the range. And then these down here are sort of you mentioned the counter examples that you're trying to come up with, but it's adding the message to sort of explain what's going on there. What's this part here about, Erik?
Those are I think those are ranges of the likelihood. Oh no, those are the modifiers. So you get 18, you get the modifier 4, 17, modifier 3. So it's basically a parameterized test.
Okay.
Yeah.
Cool. Okay, very cool. Thanks, Erik. So that's some nice lazily executed Haskell for you. which is always fun to see. And that was the last of our solutions. So I hope that was interesting. I hope you learned lots about randomness. I did, looking at this, and it was cool to see a few different languages as well. It's always nice to see some good C++ stuff, and it's really nice to see some Haskell as well. Thanks, Erik, as always, for walking us through all of those. If you've enjoyed the video, please give it a thumbs up. Please subscribe if you've not already as well. And finally, we love your comments. If there's things about this that you found interesting, you've liked, you've got some insight, we've got something wrong, please tell us in the comments. It's always great to hear. Otherwise, we'll see you for the next video soon. Thank you for watching.